everyone! In this video, we will talk about Ecuador and its population growth.
Ecuador is in South America, located on the equator between Colombia and Peru.
Its population has been increasing steadily over the years.
The population is growing because of higher birth rate and better healthcare.
This growth means more demand for job, housing and resources.
Overall, population growth affects Ecuador's development.
Stay tuned and watch the video till the end.
In this presentation, I will explain the application of the first-order differential equation in modeling population growth. Task 1 was completed to fulfill the objective of analyzing the total population in Ecuador from 1960 to 1980. The main focus of this task is the use of the Malthusian model to describe population growth over time. The Malthusian model assumes that the rate of change of the population is directly proportional to the population at any given time. This means that as the population increases, the growth rate also increases accordingly. This relationship can be expressed mathematically as dP over dt equal to kp, where pt represents the total population at time t and k is the constant of proportionality. By applying this model, we are able to estimate and understand the pattern of population growth in Ecuador during the 20-year period. This demonstrates how first-order differential equation can be effectively used in real-world application, particularly in population studies.
From the table, we have Ecuador's population data, which we obtained from World Bank's open data. We take from 1960 to 1980, and we also calculate the predicted population value from Malthusian model equation. We also calculate the percentage error of each of the data from 1960 to 1980.
To model the population of Ecuador, we begin with the fundamental assumption that the rate of population growth is directly proportional to the total population at any given time t. Mathematically, we express this as dP over dt directly proportional to p. By introducing a constant of proportionality k, we derive the first-order differential equation dP over dt equal to kp. To solve for pt, we use the separation of variables method. We rearrange the term to isolate p on one side and t on the other, giving us 1 over p dP equal to k
Integrating both
dt.
sides yields the natural log of p equals to kt plus a constant of integration c. By exponentiating both sides and simplifying the constant, we arrive at our general solution, p equals to ae to the power of kt. In this model, a represents the initial population at our starting point, t equals to 0. To make this model specific to Ecuador, we define our base year t is equal to 0 as 1960. According to the census data, the population at the time was 4,590,891. By substituting t equals to 0 into our general equation, e to the power of 0 becomes 1, which directly identifies our constant a as 4,590,891. Next, we need to find the growth constant. We look at the population exactly 1 year later, in 1961, which was 4,722,331. By setting up the equation, 4,722,331 equals to 4,590,891 e to the power of k1. We isolate k by dividing the population and taking the natural logarithm. This calculation gives us a k value approximately 0.0282. Therefore, our particular solution for Ecuador population growth is p equals to 4,590,891 e to the power of 0.0282t.
Looking at our dataset, we have defined the year 1960 as our starting point, or t is equal to 0. At this baseline, the actual population was 4,590,891. We use this actual population column as our ground truth to measure how well our mathematical model performs. As we move down the table to t is equal to 10 and t is equal to 20, you will notice a consistent upward trend. By 1980, the population surpassed 8.1 million. The predicted column right next to it shows the values generated by our formula. For the first 2 years, our model is perfectly aligned with the actual figures, showing 100% accuracy at the start. However, as t increases, a small gap begins to form between the actual and predicted values. For instance, by 1980, our model predicts 8,073,946, which is slightly lower than the actual count. The actual count for 1980 was 5,165,877. For the graph parts, this graph shows two main elements: the actual population data represented by the blue points and the estimated population shown by the red line. From the graph, we can observe that the Ecuador's population increases steadily over time, and the blue point indicate a consistent upward trend. The red line represents a model used to estimate the population growth. We can see that it closely follows the pattern of the actual data, which suggests that the model is fairly accurate. However, there are slight differences between the actual and estimated values.
From the table, the calculated values that is obtained from the Malthusian model equation are consistent with the actual value. The differences between them are very small, and the predicted population follows the same increasing trend as the actual population. The percentage error shows very small values, which indicates very small deviations between the actual and predicted value. As you can see, it keeps increasing. This is because the model assumes a constant growth rate, meaning it thinks the population grows smoothly like a perfect curve, but in real life, population growth is not perfectly consistent.
So, what factors have influenced population growth in the past? So, the first one is about healthcare improvement. Significant advancements in maternal and child health services have successfully lowered infant mortality rates over the past 2 decades. So the second one is about urbanization. So movement from rural areas to cities like Quito and Guayaquil has led to population concentration in urban areas. The third one is about cultural and religious value. So traditionally, high fertility rates are influenced by strong cultural and religious belief that encourage the larger family sizes. Last but not least, it's economic resilience. So, ongoing urban development and industrial growth has supported population expansion by creating more job opportunities and improving living standards. That's all.
There is 4 factors that may affect the population growth in the future. The first one, reproductive health education. The ongoing implementation of the Responsible Parenthood and Reproductive Health Act will likely lead to a higher birth rate, fasten up the value of K. The second one, increased education and career focus. Better education and healthcare systems can lead to lower infant mortality rates and healthier families, encouraging higher birth rates and population growth. Third, economic opportunities and stability. Stable job markets and rising incomes can give families more financial confidence to have more children, contributing to higher birth rates. Last but not least, urban development and expansion. As cities expand with improved infrastructure, housing and service, they can support larger population, allowing continued population growth instead of limiting it. In conclusion, based on the data provided, the population shows an overall increasing trend over time. For example, between 1966 and 1973 show a significant growth within a short period. This supports the idea that population growth is occurring rather than declining. The data also suggests that while growth is happening, it may not be perfectly exponential due to variation in the rate of increase across different years. Factors such as improved healthcare, economic opportunities, and urban development likely contribute to the rising population. Overall, the trend in the data reflects a growing population influenced by both social and economic factors that encourage higher birth rates and sustain population expansion.